Okay, good afternoon, everyone. I hope you're having a good weekend. And as you know that we are close to the end of this term, so there will be something I would like to wrap up and let you know about the plan for the rest of this term. We will have 2.5 weeks left, including this week. And actually, we have already finished all the preparations about the design of the pavements. The rest thing left for us to play is the how to conduct the actual design, while including design for the flexible pavement and the rigid pavement. So the schedule is like for this week, we will work through different measures for the flexible pavement design. And the next week, we will go through the rigid pavement design. And of course, I want to leave some time for the review of the final exams. And if you have any questions, feel free to raise your hand or leave your questions in the meeting chat or drop me the email. And I will also upload the last homework assignment, which will be related to the pavement design, the rigid pavement design and flexible pavement design. I do not expect you to finish them this week because we will just introduce this one. You will have plenty of the time to work on the homework assignment. So before I go to the lecture, do you have any questions so far? And also, if you for the lecture last week, especially about tutorial of the CAMPAVE, I hope you have the chance to go through the videos by yourself, and with that you will be able to learn how to use the softwares to improve your the computational efficiency. So okay, if we don't have any questions, I will share my screen and start lecture today. Okay. Okay, so in this lecture, we're gonna start the topic, the new chapter about the flexible pavement design. And this one will tell you how to design the thickness of different pavement layers and how to select the structures for the flexible pavement. And of course, we're going to introduce different measures, the general measures, which will include the AI method and the ASHTO method, which will be there are two most common methods. And we're going to see how this method will be adopted for the pavement design in Ontario. First of all, to make it general, we will start with the design concept. Usually there will be three types of the design methods, three categories of the design methods, including the empirical method and the mechanistic methods, and there will be something in between the mechanistics and the empirical methods. For the empirical method, we will only use the experience or the historical information to finish the design. Well, for the mechanistic method, we're gonna try to analyze the response of the pavement structures with respect to different load and try to utilize some theoretical features of the materials. And the mechanistics and empirical method, which will be something in between, we'll combine both of them. So as I just explained, for the empirical designs, it's based on the results of the experiments or the experience in the past pavement design. And it requires a lot of observations and collections about the data in the field. And then we will try to establish the relationship between the design variables and the actual performance observed in the field. It's more like you will develop a statistical model to conduct the design directly. And as this is only based on the observations, So it's not necessary for you to establish any scientific basis for this relationship. It could be something unreasonable, but that's all common. That's also one potential drawback of the empirical design. It's able to simplify your design work, but it cannot extend this design to the other areas. There will be some typical empirical design methods. In Ontario, we have the MTO, the earlier version routine design. We have the CBR thickness design and ASTO 1993 design. Those are the common method applied for the pavement design in earlier years. But for nowadays, we will prefer to use the ME design, the mechanistics and the empirical design. So it will combine the advantages of both mechanistic and empirical designs. With the empirical design, you can get some real-world information, real-world data, and the features of the pavement structures. And with the mechanistic component, we can determine the response of the pavement to different loadings with some mathematical models, as what we explained previously about the stress and strain analysis of the flexible and rigid pavement with the closed form solutions. And this will be the physical properties of the materials applied for the pavement design. While for the empirical components, it will show the real-world response to the performance of the pavement. And for the combination of this one, we are able to analyze the key distress types associated with the critical pavement response, and then we can find out an appropriate schedule or find out an appropriate thickness of the each pavement layers to support the load for longer time, and to find out the appropriate frequency to do the reconstruction and maintenance of the pavement structure. So that's the advantages of utilizing the ME design. Basically, can combine the advantages of both mechanistic method and the empirical methods. Usually, for the pavement design procedure, we need to consider several important factors. We need to do some experimental investigation in the lab to understand the properties of the materials that we're going to use for the pavement, and we have to know the way to improve the pavement analysis procedures, like how we probably can use some softwares to conduct the pavement analysis, and also the way for us to improve the pavement material characteristics, like how you're going to improve the stiffness of the materials to support the bottom layers, how you're going to try to improve the resilient modulus of the subgrade layers, and so on. And also we need to consider the national and regional pavement performance studies to understand the different requirements at different regions, like the design in Canada, in northern Ontario will be different from that in the southern Ontario, due to the weather conditions, due to the protocols applied at different regions. And for basically, if we want to compare the ME design with the other type of the methods, we can see the clear advantages. For the ME design, we will not only identify or calculate the thickness of each pavement layers, we will also make a comprehensive approach to consider the structural features of the pavement, to consider the properties of the materials, and we also can provide some guidance to do the rehabilitations for the pavement structures, and try to do the maintenance in the future. And we also are able to deal with the impact of the weathers, the moisture contents, the temperatures, the frost heave effect, and so on, and try to make sure that the design is reliable for the design life. So those are all included in the ME design. And this figure actually shows the flow chart for the design of the flexible pavement. We will start with the weather climate models, where we're going to try to think about what's the impact of the climate to the to different type of the material, to different the properties of the materials, including the hot mix asphalt, the base and subbase soils and materials, and subgrade layers. And also we want to include the traffic loadings to identify the volumes or to estimate the ESAL for the designed pavement structure. Both of them will be contribute to the material properties. And then we will put all these factors together to do the analysis about the stress and strain, and try to utilize the pavement structures like the what's the thickness of each layer, what kind of materials you're going to choose, and do the analysis. And we're going to make a prediction about the distress to see how, at what condition the pavement will be failed, and how we're going to handle it if the pavement structure is not appropriate. Probably we need to increase the thickness, or probably need to change some stronger materials, and then redo the distress predictions to make sure that it's able to support the designed traffic load for the design period based on the consideration of the climate conditions. So this one is an overall flow chart about the pavement design. Basically, it will include all the previous topics that we have introduced in this class. And with that, I will first start with a very simple method, which is the MTO routine method. This is one kind of empirical method. It's very simple. It's applied for some of the road in Ontario for now. And this one is actually we have several versions. As a first developed by MTO in 1990s, and then try to utilize some of the results from the ASTO 1993 method, and eventually they have a standard procedure for the routine method, which would be the MTO 2008 version. This method is very simple. It only needs to consider as 4 different type of the informations. The first one would be the ADT and the class of the road. The ADT will represent the average daily traffic, the number of the vehicles were traveling on the road every day, and the class of the road, whether it's in the freeways, as in the local major arterial corridors, or the residential areas, or anything else. We also need to think about the subgrade materials, what's the percentage of the fine particles, the clay particles, and so on. And the drainage and the frost effect will also be considered, but it's not included as a direct factor. Instead, it will be considered indirectly. And in this routine method, one of the key variables you will consider is called the granular base equivalency, which is abbreviated as the GBE. It will try to identify the equivalent factor for different layers based on the materials we select. For example, usually for the hot mix asphalt, the GBE will be 2. This indicates that the 25 millimeter hot mix asphalt will be equivalent to a 50 millimeter granular base layer. So this is 2 times higher. If it's a base, it will be, if the parameter is 1, then it just means that 25 millimeter base will be 25 millimeter granular base. And for the subbase, usually it's smaller than the value is less than 0 or less than 1. It indicates that the 25, for example, if it's 230 indicates that 25 millimeter subbase is only 17 millimeter granular base. So they will try to find out a way to find out the equivalent thickness in the granular base for all the layers applied for the flexible pavement. And this one is quite convenient for you to make a quick check about whether the design is appropriate or not. The routine method is widely applied for a lot of Ontario roles, and it's used for a quick check instead of the actual pavement design. Because you can just utilize the GBE to quickly check what's the thickness of the granule base, and then find out whether it's under the appropriate range. If it's within the range, it means that it's appropriate for that for the design. If it's not, you need to think about whether you need to increase the thickness of some layers or not. So there will be some typical GBE factors for different type of the materials. If you are working on the new pavement projects, then you're probably going to use the hard mixed asphalt. Then the GBE will be 2.0. For the granule base is 1.0. The granule subbase is 0.67. Well, the granule subbase will have the CBR less than 60. And for the OGDL is not recommended, but the value is only 1.0. And if you are doing some resurfacing project, try to do some maintenance about the pavement, the existing pavement structure. The old hard mixed asphalt will be the GBE will be 1.25. For the granule base, it's 0.75. For the old granule subbase, that will be 0.5. So we will have the significant reductions about the older materials. But if we are working on the reconstruction and still do the utilize the or recycle the older materials, you will see the further reductions about the GBE factors. For the older hard mixed asphalt, that will be 1.0. The granule base is 0.6. The granule subbase is only 0.4. So this would be some typical GBE factors for different type of the materials applied for the different pavement projects. And here would be some recommendations. One example is about the Kings Highway and freeways. It tells you what's the thickness you will be assigned for the pavement depending on the average daily the annual average daily traffic and the subgrade materials you select. For example, for the ADT higher than 4,000 vehicles, then you need to think about the design in this row. And depending on the subgrade materials that you have to select for the pavement design. If it's in the gravel and sand suitable as the gram borrow, then you need to think about a design with the hard mixed asphalt for the thickness of 130 millimeters, for the granule base 150 to 250 millimeters, and you don't need any subbase. And in general, with that, the GBE for all the pavement structure will be around 410 to 510 millimeters. And if you have the other type of the materials, for example, for the sand and the silts, say that if the percentage of the sand and silts is higher than 55%, then you will have the other type of the design. For example, if we consider an ADT of 3,000 to 4,000 vehicles per day, you should select this kind of design. For the hard mixed asphalt, you need to select the thickness between 120 to 130 millimeters. For the base as 150. For the subbase as 600 to 800 millimeters. So here you can see that you can actually find out the GBE based on all these three values. Say that if the H for the GBE hard mixed asphalt is at 0.0, for the B that is 1, and for the subbase as 2/3. Then for this specific case, the total GBE for all the 3 layers, that will be say that 120 times 2 plus 150 plus times 1 plus 600 times 2/3, and will give you the value around 790. So which would be a low bound, and you can also find out the upper bound based on the suggested thickness. You can also find out the design for the other traffic levels and also the different type of the subgrade materials. If we choose to use the routine method, that's what we need to do. We just try to look up this table and then select the appropriate thickness for each layer. And here, let's go to see one example. Assuming that we have the average daily traffic of 1,500 to 2,000, and we have the this would be in the 2-lane secondary road, and we have the 50% of them could be the silt or the fine sand. And then if we go back to check the previous one, check the previous table, you will be able to find out the appropriate design. First, you need to identify what's the average daily traffic. So for the traffic is 1,500 to 2,000. So what you get is around this category, and you also can find out the fine particles is around 15%. So that will be this column, and with that you can easily find out the design. With the hard mix asphalt as 50 millimeters, the granular base as 150, and the granular subbase as 300. And you can then calculate the GBE, as the total GBE for those design. Assuming that we have the factor as 2.0, 1.0, 2/3. In this case, that's 50 times 2 plus 150 times 1 plus 300 times 2/3, which will give you the value as 450 millimeters. So that will be the equivalent thickness for the granular base. So this would be one example about how to use the routine method to complete the design. And we also have widely applied the method for the in some local areas. For example, for the city or the Mississauga, they have the implementations about the routine method, and they specify the minimum pavement and the road design requirement. What's the minimum thickness for each layer? Depending on the design is depending on the type of the road, or the class of the road. Basically, for different type of the class, it will have the different volumes. For the arterial and industrial road, it means that it will have a higher volume, higher traffic, and for the residential road, the traffic will be low. And also, you will consider the first susceptibility for the design, which will be considered into 1, 2, 3, 4, 5, 6, considered into 6 groups. And depending on the first susceptibility factor and the type of the road, you can then select the minimum thickness for each layer. For example, if we are considering the arterial corridor, which would be the major local road, with the first susceptibility factor of 7, then you have to choose the minimum thickness for the hard mix asphalt layer as 85 millimeters, the minimum granular base course as 150 millimeters, and the minimum total road structure length as 610 millimeters. So this is the total value, including the granular asphalt layer, the granular base layer, and subbase layer. So that's the instructions, the protocols applied for the city of Mississauga. And now you may have any questions about what is the first susceptibility factor? How can we determine it? In the city of Mississauga, they actually consider the utilizing the percentage of the fine particles in the subgrade materials to determine the susceptibility factor. This table shows the way for you to identify the first susceptibility factor. It depends. The factor is estimated based on three portions about the materials, including the percentage of the sand, the percentage of the clay, and the percentage of the silt. And it will actually, this triangle is actually divided into 6 regions. So we will have the this part would be the processability factor of 1, and this region will be 3, and the one on top, that's 5, and in between, this is 7. So including all these regions. And then you have the region for 11 and the rest for the 15. So now I'm going to show you one example to see how we can identify the this first susceptibility factor based on the portions of the particles in the subgrade materials. Let's consider one example. Say that the subgrade consists of 20% of the clay, 40% of the silt, and 20% of the sand. So what you need to do, you need to first identify the line with respect to 20% of the clay. So this would be the 20% of the clay where I can find. And there will be 2 lines. One is going through the left, the other one is going downwards. And the next thing you need to do is find out what's the percentage of the sand. The sand percentage is also 20%. Sand is also 20. So this side will show the percentage of the sand. So you have the 20%, and then you need to find out the line which will intersect with the 20% of the clay contents. So this will give you the value. Choose the line here, and from the clay. So they will intersect at this point, and you can find out that the rest of the 60 will be the silt. By finding out the intersection of these 3 lines, you can find out which point we have to consider. So in this case, this is the point we will choose for the selected subgrade materials, and you can clearly find that it's the first end of the region of 15. So the first value is decided as 15. And so that will be the all about the routine method. With that, I want to pause for a couple of seconds to accept any questions. Do you have any questions, concerns about this method? This is one kind of the empirical method, and it's also easy for you to design if you don't have any additional information provided. Any questions so far about this topic? Okay, if we don't have any questions, I will jump to the next one about the a more common method applied for the flexible pavement design, which is called the AI method. And the AI method is also an empirical method. The one is actually developed by the Washington Department of Transportation and also AASHTO, and it's developed a long time ago and further revised in 1981. Based on some mechanistics and empirical analysis, and also later on do some further improvement in 1999. And this one, the design of this method will try to make sure that the thickness of the pavement structures is designed large enough to limit the to try to support the repeated horizontal strain at the bottom of the asphalt concrete so that it can avoid the fatigue cracking. And in the meanwhile, we will try to restrict the vertical strain at the top of the subgrade so that it can avoid the permanent deformation. Though this would be the two major distress of the flexible pavement. And the AI method will try to overcome the failure from these two distresses, fatigue cracking and permanent deformation. And it will also, with this design, we will also try to check the potential alligator crackings. If it's below 20 to 25%, it means that the pavement is still under the service. For the rotting, if it's less than 12.7 millimeters, means which is a half inch, means that it's the rotting is not severe. So the serviceability of the pavement is still be good. So we will try to make sure that over the design life, the alligator cracking is always less than 20 to 25%. The rotting is always below half inch. So that's the whole idea for the AI method. And then let's go to show you. Let's go through some details about what we need to think about for the AI method. First of all, the AI method is here. The AI method is applied for the flexible pavement design, and from our previous analysis about the stress and strain of the pavements, we can see that the load will be transferred through the pavement structure. So say that the flexible pavement structure, and it will transfer to the subgrade. If we consider the two layers, usually we will have more than two layers for the flexible pavement, but we can consider the base and subbase layer will be consistent. So for the hard mixed asphalt, the asphalt layer, at the bottom of the asphalt layer, we need to think about the tensile stress. So the tensile stress between the asphalt layer and base layer, we want to make sure that the design or the thickness of the hard mixed asphalt layer is high enough to sustain all the tensile strengths during the design life, so that we can prevent the crackings from the hard mixed asphalt layer. In the meanwhile, we want to make sure that the compressive stress at the intersection of the base layer and the subgrade layer is small enough so that we can prevent the deformation. And this would be the two critical criteria we're going to select for the AI method. And now in the design, we will need to think about how the two type of the crackings are actually generated. For the fatigue cracking, it usually comes from the repeated loading and the horizontal stress at the bottom of the asphalt layer. And if it exists the capacity of the asphalt layer, then we will have the cracks. And for the rotting or the permanent deformation, it will usually occur at the surface of the asphalt layer, and which will usually be caused by the deformation of the subgrade layer. And we also need to make sure that this one is small enough to make sure that the pavement is smooth. And also we were considering some perfect construction work, but the rotting can also be caused by some construction problems such as the inadequate compactions about the subgrade layers, and so that's also the reason we want to follow the compression protocols to do the to smooth or to process the subgrade layer. And we also need to understand what's the features or the characters of the subgrade soils. And for the AI design, we will consider we'll usually consider the three different type of the layers: the asphalt concrete surface over the asphalt concrete base layer, and this is actually called the full depth applied for the full depth structure. And we also will consider the emulsified asphalt concrete surface over the untreated granule base, and this is usually applied for the deep strength pavement. And the third one would be the untreated aggregate base. Again, both of them will be applied for the untreated for the deep strength asphalt pavement. And this figure actually shows the two different type of the pavement structures, flexible pavement structures designed by the AI method. The full depth asphalt pavement, we already has the asphalt concrete surface. Usually this one is very strong, but the thickness will be small. And then you will have the asphalt concrete or the emulsified asphalt base. For the full depth pavement, the thickness of the emulsified asphalt base layer would be very large, and then both layers will be placed on top of the subgrade. But for the deep strength asphalt pavement, the structure is different. For the deep strength design, we will have the asphalt concrete surface layer, which will have the similar functions to the full depth asphalt pavement. It will be strong and it will be able to support a very large load. And below that one, it will have the asphalt concrete or emulsified asphalt base. And the thickness of this layer is relatively smaller compared with the full depth asphalt pavement. And then behind the asphalt concrete layer, we have a very large thickness of the granule base layer, which will use some granule materials, some sand, some crushed stone, for the development of the or the construction of the flexible pavement. And clearly, this one for the deep strength, for the full depth asphalt pavement, the total thickness will usually be smaller than the deep strength. That's also the way for us to define their names. One is called a deep strength, the other one is the full depth. And in the AI methods, one of the most, as what we explained previously, one of the most important factor we have to consider is about how to design how to select the thickness of each layer to make sure that it can support the fatigue cracking. They can prevent the permanent deformation at top of the subgrade. Actually, there will be a lot of analysis about the design criteria. Usually for the fatigue cracking, we will have a relationship to represent the fatigue as a function of the strain and the modulus of elasticity. And the here this is one common statistical model to show the relationship, and the one below is another model, comes from the share company. They do another analysis to calibrate this model and find out the relationship. And the second one would be the prominent deformation at the top of the subgrade. Again, they will also have an empirical statistical model to show the relationship between the deformation and the vertical stress at the interface of the subgrade layer. And the usually we see that the maximum allowance is only ½ inch. So both of them will be some empirical models, and we're gonna need to analyze to utilize the calibrated model to analyze what's the fatigue cracking, what's the prominent deformation for the design thickness of the pavement. Once you have identified the tensile strain and the vertical compressive strain. So this would be the design criteria. And the next thing for the AI method is about the traffic conditions. This is what we what we just learned in the traffic volume and traffic loading and volumes. I will just give a very quick review about it. So basically, for the traffic analysis, we need to identify or calculate the ESAL, and in order to calculate ESAL, we need to identify the load equivalency factor for each type of the vehicles. And then once you have the load equivalency factor, you're gonna be able to find out the ESAL by summarizing the values for all different groups. And those values will be related to the initial number of the repetitions per day, the directional distribution factor, the length distribution factor, the design period, the growth factor, and and also the annual growth rate. So we have already learned this one, so I will just skip the details here. Also, you can find out the equation to calculate the ESAL with the equivalent 80 kilonewton single axle load, and here you will be able to identify. You can find out the definitions of each component for the estimation of ESAL, and also the estimation of the track factor based on the load equivalency factor. I will skip this part. This is what we have learned previously. Well, for the AI methods, there will be some sample values or typical values about the load equivalency factor. Usually, with the AI methods, the load equivalency factor can be determined by this equation. The LEF is the ratio of the actual load and 80 kilonewton, that will be the standard load to the power of 4. And if you go to check the table on the right, you can see the value here. See the load equivalence factor for the single axial load and tandem axial load. For example, if you have a load of 40 kilonewton, you can find that the LEF for the single axial load is 0.0562. If we have the standard load, definitely the value will be 1 if we go back to check this equation. But for the tandem axial, it's different. It's a tandem axial. You will have the 4 tiles for each axial, and definitely means that the load will be or the load applied to the pavement will be smaller. That's the reason you observe the 0.0773 LEF, and you can also find out the other values. You can find out something very large for 356 kilonewton. Then usually it's not applied for the single axle, but for tandem axle, you can find out LEF is approximately 29. So that's the LEF for different type of the load with the AI method. And also there will be some general for equations to calculate the LEF. There's one thing called the France Pavement Design Manual. It will define LEF as K times axial load divided by 80 to the power of alpha. So here we have two factors, K and alpha. And usually for the flexible pavement, the alpha would be 5, and for a single axial case 1, tandem is 0.75, trident is 1.1, and for the rigid pavement is different. Alpha is 12, single axial K is 1, tandem K is 12, and trident is 113. So that's the LEF, a general formula, and it can also be related to the subgrade stiffness and the asphalt layer thickness. For example, if the stiffness of the subgrade materials is 60 megapascal, and the asphalt layer thickness is 0.1 meters, then you will have different parameters, different values about K. For example, for single axial, single wheel, that will be 6.26. For a single axial dual tile, that will be 1.0. This is the standard. And you can find out the value for the other type of the axial, the wheel construction, wheel combinations. So that's the LEF. Just let you know that there will be different type of the LEF, different type of the models for you to calculate the LEF. But generally for the AI method, we're going to use this one, use this equation to do the calculation. Okay, and there will also be some maximum legal load applied for different type of the the axial configurations. For the single axial, single wheel, single axial, the maximum load will usually be around 58 kilonewton. For the dual wheel single axial, it's 98. For the tandem axial, definitely you can get a larger load, but there will be some maximum value here. You usually will not exceed this maximum value for the existing design of the truck. And in addition, we will also have some typical ranges about the ESAL for the design life with respect to different type of the road. Generally, AI method will categorize the traffic into 6 categories. For the category 1, it will usually represent the parking lot, the driveways, or some light traffic residential street. The ESAL will be around the 5,000, and usually the number of the heavy truck will be less than 7,000 for the design period. And by increasing the traffic classes, the volume increases. And for the last one, for the class 6, it will have the ESAL more than 10 million, and that could represent the urban intersection freeways, some industrial roads, and you will have a lot of trucks, could be around 10 to 15 millions over the design life. So this will be some typical values about the ESAL applied for the that we're going to use for different type of the road. And this one is also related to the tire pressure. With the higher tire pressure, usually indicates that the load applied to the road would be larger. So if your tire pressure for the truck is larger, it means that we're gonna have to increase the load equivalency factor. Generally, the standard tire pressure is around 70 psi. Usually the contact pressure or the tire pressure, it's only 0.9 90% of the inflation pressure of your tire. By increasing the tire pressure, the ESAL adjustment would be larger. For example, if your ESAL is 100 at 70 psi contact pressure, then at 100 psi, you probably need to increase that one to 400, 4 times larger. So that's the that's something we also need to consider if we are provided with the tire pressure. So I guess I don't have enough time to cover the rest, so I will stop here. Do you have any questions about this topic? And of course, we're going to try to finish the rest contents in the next lecture. Any questions? Okay. If no, then that will probably be all today. And really appreciate your time for the class. And just let me know if you have any additional questions, any concerns. Feel free to send me email. Okay. Okay, I think that's all. I guess if you don't have a question, I will close the meeting and I will see you on Wednesday. Okay, that's good. Thank you very much. Enjoy your day.